Hey, all right, we are live. Um, all right, welcome to this new episode of the Rust live coding session with the B team, episode 10 this week. This week, actually, I'm not going to code that much. I just wanted to take some time and explain one of the core features of Chrysalis Part 1, which is white flag. Maybe I'll be doing some code, but mostly it will be actually explaining the feature, doing some review of the code that has already been written, and trying to answer some questions if you have in the chat. So where we are at the moment in the B team regarding white flag, we finished it this week. It definitely needs to be polished a bit, to be fully tested, to be fully documented, but it's working fine. It's been tested on the comnet, on the mainnet, so it produced the right ledger state, so everything is going fine. So at the moment the goal is to actually release something next week for some community members to try this feature live. So yeah, I just wanted to start with presenting this new website we have for the protocol of IOTA. So this is the IOTA protocol RFC book. It is automatically generated from the repository IOTA lecture GitHub. So if you are not aware of that, we have this repository where basically we create pull requests to do some changes on the protocol level of IOTA, and automatically when a new PR gets merged, it triggers an update on the website. So it's a more convenient way for everybody to have a read of all of the changes of the protocol. So it has been started quite recently at the start of this year, so you don't have all of the features of the protocol inside, but starting from the beginning of this year, you have all of the changes of the protocol. So for example, you can see white flag, which is what I'm going to explain today. You have this WRTS, which is the new tip selection algorithm. Sorry. We have the milestone Merkle validation, which is kind of part of white flag. I'll explain a bit this one as well. And we have this binary to ternary encoding, which is a new encoding that is needed by the new milestone Merkle validation. So yeah, this website is very convenient. You can navigate with the arrows. It shows very nicely in Markdown, so yeah, pretty nice. So yeah, what's white flag? White flag is a new way to compute the ledger state in Chrysalis Part 1. So if you know how was the if you know was computed the ledger state in the previous version of IOTA, for information, we released white flag. As part of Chrysalis Part 1 2 weeks ago, so it's very recent stuff. But prior to that, the ledger state was computed in a very different way. So the major difference introduced by white flag is that we now allow conflicts to be part of the confirmation set. What it means is that if two bundles are conflicting, for example a double spend, previously we didn't allow that in the confirmation set. So the confirmation set is the set of all transactions that are referenced by a milestone. And previously we didn't allow to have conflicting transactions in this confirmation set. So what it means is that it was really complex for the coordinator, for example, to check to create a milestone, because it had to check that the trunk and the branches didn't indirectly reference conflicting transactions. So if that was the case, then it couldn't produce milestone, and it had to get another set of tips and do that process until it finds 2 tips that are not conflicting. So it was a really expensive process because you had to do a tip selection algorithm. So choose a trunk, choose a branch, and then do a traversal on both and find if the passcon of both you didn't have something conflicting. So obviously it means that you had to do a lot of traversals in the tangle, so something that was really expensive. Now with white flag we do allow conflict in the confirmation set of a milestone, but we just don't apply them to the ledger. So we just apply the first of the 2 conflicting bundles. But who says first says ordering. So we have to enforce a specific ordering of the tangle to be able to say which was the first transaction. Because when you have, for example, a blockchain, it's pretty obvious what transaction came before which one, because they're all chained. So you have a very logical path. But when you have something like a graph, the tangle, for example, it's not that obvious to say what transaction was the first, because you have a lot of reference, so it's not that obvious. So you have to enforce a specific ordering of the tangle so that all of the nodes have the same view of the tangle and they are all able to say, hey, that was the first. So yeah, I'm just going to go through the RFC quite quickly. Yeah, so just going to the motivation why we ended up doing that instead of the previous one. The previous version was subject to what was called the conflict spamming attack. But basically what that means is that since you couldn't have conflicts in the confirmation set, if someone was spamming conflict, then it would be very hard for the tip selection algorithm to select tips that are not conflicting. And then in this picture, for example, you have 2 conflicting bundles, and whatever was attached to it would be discarded because they would be invalid, because validating something that is a conflict. So what it means is that both of these sets in these circles would be denied, one wouldn't be confirmed, and then you would have to reattach them again. So on the previous version of IOTA, the confirmation rate was a bit lower than it is today because of this specific issue. Now if you go to, for example, thetangle.org, you should see something that is nearly 100% confirmation rate, because now you confirm absolutely everything. So you have the guarantee that your transactions are going to confirm. So we don't have the need to reattach as much as we had before. So now this conflict spamming attack doesn't exist anymore in the new version of IOTA. Yeah, so as a consequence, it's now way faster to do tip selection algorithm, because you don't have to check for conflicts while doing tip selection algorithm. So now it's way faster. Alright, I spoke about that. This is just some definitions, so I'm not going to speak about it. But yeah, what I said is that we have to have a deterministic order of the tangle. So that's the first major part of white flag. So we chose to do a topological ordering, which means that you have to have the dependencies before what depends on them. So it's just basically a DFS. It's a post-order DFS by going through trunks first and then branch. So that's the topological ordering we settled on. So we first always go to the trunks, and then we first always go to the branch. And in trunk and branch we do a DFS post-order. So post-order DFS basically means topological ordering. So you are sure to have all of the dependencies nicely aligned. And then when you do that, when you do this ordering, you get a set of bundles, and you go through this set of bundles and you start applying them to the ledger. And if when doing that you come over a conflicting bundle, you just don't apply it to the ledger. So that's how it works. And here you have some Sorito code, and then here we have a picture to illustrate an example. So here you have three different colors. You have red, you have purple, you have blue. They are all sets of confirmed bundles by a milestone. So here you have the milestone H, you have the milestone V, and here we are interested into ordering the set of purple bundles validated by the V milestone. So if we do what we said, we first go to trunks. You have the legend there, so you know that trunk is the straight row and the dashed row is the branch. So if we do that, we first go to trunks, 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 and the first milestone in the set would be D, and that's what you see here. So I'm not going to do the complete set, but if you go back from D, then you have G. If you go back from G, you have L, and then from L you have a branch, so you have J. So that's what the set starts with. D, G, J, L, M. So now you have your first set, and in the second picture you have a conflict. So bundle G and bundle O are conflicting, and the first one that appears in this set of ordered bundles is G. So that's the one you are going to apply to the ledger, and then you just ignore O. Yeah, and that's pretty much it. It's a very simple algorithm, way simpler than what we had before, and it's also way more efficient. So yeah, basically only pros for this approach. But there is a question in the chat, but what if they have the same height? It doesn't change anything. It doesn't change anything that they have the same height, because there is only one ordering possible, and it's the post-order DFS trunk branch. If you apply this ordering, you will always have a first transaction and then a second transaction, even if they have the same height. So for example, let's say D and E seems like they have the same height. D would still, well, that's a bad example because E is not in the same milestone, but let's say for example, yeah, L and M have the same height here, but given the ordering, L would always, so what do you say, G and I, well, the example you give, J and I, yeah, they have the same height, maybe, I haven't checked, but if you do this specific ordering, you clearly see that G comes before I, so G would be applied and not I. So it doesn't really matter about the height, you just compute your ordering, this very specific ordering, and then you just apply whatever comes first. I hope that answered the question. Yeah, tell me if that answers, and I'm just going to go back to the code. Alright, so now in the B repository we have this B ledger crate. That's where we have the white flag code. At the moment, there is some modules. There is some modules that are not specifically tied to white flag, and then there is the white flag module. So I'm just going to go through what is not white flag. So we have some small definitions. So we have the ledger state. The ledger state is nothing more than just a hash map of address and use64, so an address and a value. So that's what you basically expect from a ledger. That's just if you have an account model, which is the case at the moment. So just a hash map, address and its associated balance. And then we have just two convenience methods that we are going to use a bit later. So this one, get or zero, is just a way to have the balance of an address, and if there is no balance, we return zero, which is very convenient when you compute, when you do some addition or whatever, so that you don't have to actually check if the address exists or not, if it has a balance or not. So we return zero even if the address doesn't exist or anything. And then we have this one. Maybe I'll just speak a bit about this one because I really like this API. So it's just a method to apply a difference to a specific address. So instead of U64, it's an I64 because it can be negative as well. So if you send some token, you would do an apply with a negative balance. But yeah, I just want to speak about this entry API because I really like it. Because if you want to do an apply but you are not sure if the address exists at the moment, you would have to first do a check if it exists. So you would end up doing two hash map access. The first one to check if it exists and the second one to actually update it. But you don't have to do that with the entry API. So you first get an entry, but the entry potentially doesn't exist. And then you have some method. So you have endModify that takes a closure that will only be executed if the entry actually exists. So so this one is basically the case where the address already existed. Then you have the closure with the pre-existing value, and then you can just apply your difference to it. And you can chain an OR insert method, which is basically the case where the address didn't exist. Then you don't have any addition to do. You just insert the diff. So yeah, I really like this API. And then we have a diff, which is basically the same thing, but with I64. So this is something that, for example, is generated by a milestone. When a milestone is confirmed, it would generate a ledger diff, which is the view of all the differences of all the addresses value that has been created by this milestone. And that's probably something that we want to store in database. So yeah, we have this ledger diff. Then we have this one, which is an event that is created by this create whenever a milestone is confirmed. So it's basically done so that plugins that want to do some analysis have some data to work on. So whenever a milestone is confirmed, we publish that, and all of the plugins that registered for this specific milestone, for this specific event, have access to it. So they basically have the milestone, so it contains its index and its hash. Also the timestamp of the confirmation. They have the number of tails that have been referenced. They have the number of zero value bundles that have been referenced. They have the number of conflicts that have been referenced, and they have the number of tails that have been actually included in the ledger. So some data so that they can work on. And we have just the lib.rs that that declares all of the other modules. Alright, and now let's have a look at all of the white flag modules. Alright, just a going to do that. Alright, so this is the main module. So it's going to basically declare the init function so that the node can initialize white flag. So basically what it does, the whole white flag will be a worker. So it's, if you know the actor model, it's basically an actor. So it will hold some data, and you can communicate with it. Via channels. So we need to create some channels. So this is the event channels, and this is the shutdown channel to be able to shut down the actor. We basically register the ledger worker, so the white flag worker, to the shutdown object, so that when the node shut down, it can send a shutdown signal to all of the registered worker to have a graceful shutdown of the whole node. All right. See it. Then we create so this may seem weird, but this is a global static mutable object, because when we deal with an event callback like this one, we need to have access to a channel, but the channel needs an owner. It needs to be stored somewhere, so we have to do this static object. But now that I look at it, I think this field doesn't need to be here. I think this is just something remaining from a past implementation of this white flag, but maybe we'll come back to it. But I think this can be moved to the worker and not be here. So we actually spawn the task when we register it to the shutdown. So we spawn the task, so now it's actually running. We create this static object, we assign it. Unfortunately, it needs to be an unsafe operation, because changing a static mutable object is unsafe. But the important thing is that what we do is that we register a new event listener, and what we are interested into is this specific event, last solid milestone changed. So this is an event that is created by the protocol crate. So I'm going to see the events of the protocol crate. We have 4 events, but the one that is interesting here is this one, last solid milestone changed. So what it does is that whenever a new solid milestone is created, so whenever we solidify a new milestone, we fire an event, and white flag is listening to that, because the only thing that white flag wants is to confirm milestones as soon as possible. So it listens for new solid milestones, and whenever it has new solid milestones, it sends a message. It sends a confirm message to the worker so that it can validate this specific milestone. So, and that's basically what the initialization method does. First, it spawns the worker, and it registers to this specific event, and it sends, whenever that happens, it sends a confirmation message event to the worker. Alright, we'll see this one a bit later, but I haven't spoke about this one. So the fact that now we are allowing conflicts to be part of the confirmation set came with one little disadvantage, because when you boot a node, when you load a node, it starts with a snapshot file. So a snapshot file is basically the ledger state in a file. But what happens if this ledger state is corrupted, or if you downloaded it from a source that has been attacked or whatever? But if ever you boot a node with an invalid ledger state, in the previous version of the protocol, it would be automatically detected, because whenever there would be a conflict, the node would stop, because that's not something that was allowed by the coordinator. But now that we allow conflicts, you wouldn't have any way to know that your snapshot file was corrupted or attacked or whatever. So we had to do something more, which is another RFC, milestone Merkle validation. So basically, what this RFC proposes is to include in a milestone bundle a Merkle proof of what has been integrated in the ledger. So the coordinator creates this Merkle proof, it puts it in the milestone bundle, and when you validate, when you try to confirm a milestone, you extract this proof, and you also compute the proof from your own view of the tangle, and then you compare both proofs. So at some point, if there is an issue with your snapshot file or any kind of other issue, you wouldn't have the same proof as the coordinator. So, and then you can stop the node and say, log a message or whatever, and say that there is an issue. So basically, I'm not going to read the RFC completely, but basically what a summary is that you do a Merkle proof of a list of hashes that have been integrated into the ledger. So whenever you have a bundle that actually mutates the ledger and is not conflicting, you push it to a list of hashes, and at the very end, when you have finished your traversal, you compute this Merkle proof, which is just a Merkle tree. So it looks like that. So you hash on top by pair, you hash, and at the end you have a Merkle root, something like that. So you just end up with one hash, but it contains all of the history of what has been integrated into the tangle. So at least one tiny change would have an effect on the final hash, so you will be able to be notified by that. So this module takes care of that. It's a very simple module. So basically, you have this Merkle hasher. It has a generic parameter, which is a digest function. So it's generic, so it could be whatever implements this digest threat. So this is a very common threat when you deal with cryptography or whatever in Rust. So it proposes a set of different methods that you would have to implement, very common methods. So it's generic over that, but for the case of the milestone, we use Blake to be. So that's a hash function. So what happens is that we start with this function. So as I said, we take a list of hash, and what happens is that depending on the number of hashes, we don't execute the same function. So if there is only one hash, you do the empty hash. So you just digest an empty hash. If you have just a leaf, then you just it means that you have only one hash. Then you just hash the hash. So you just digest the specific hash. And finally, if you have more remaining hash, it means that it's a node in the tree. So basically you split it according to a power of 2, and you hash the left part and you hash the right part, and it's basically a recursive function because you are going to hash it again, so execute this hash again. So at the end you are always going to end up on either an empty hash or a leaf hash. Alright, yeah, I just saw something. I see that we are doing 2vec a lot. 2vec is allocating from something, so it's going to create a vector out of something, but there is probably a way to avoid that, because we return that and then we directly use it there. So I am not sure if we first need to know what digest return, for example. Rust digest thread. So this is the thread I'm talking about. What was the function? It's digest. Alright, and it returns output. I'm not sure what output is. Output is type def on generic array. I'm not sure what that is. But it seems like it's an owned type, because it seems like it's just a wrapper around an array or something like that. So it's already owned, so we shouldn't have to actually convert it to a vector, maybe. Digest output. So maybe we need to, right. So I'm just trying to do less allocations here, because it seems like there is no need. We already have an owned version here, and then we are doing another one here. So basically means 2 allocations in a row. So it shouldn't be necessary. So output. Alright, and it has a generic parameter which is the actual digest function. Alright, so we should be able to do something like that. And the generic parameter it wants is the actual generic parameter of the Merkle hasher itself. So we should be able to just do something like that. Alright. Alright, so it seems to be working. There is an error here because all the branches of the match doesn't have the same type. So maybe we can do the same here. Alright. Alright. Yes. So now I'm not going to change the output type of this one, because this is the actual API. As you can see, these 3 functions are private, and this one is public to the crate. So this one is the actual API. So I still want to have a vector of U8, so I'm not going to change this one. So I'm just going to yeah, so this is the right, so this is working. So we only want to convert to vector the output, the last result. But I'm still wondering about this, because this is still going to create some maybe we could improve that as well. Alright, still this is already some allocations less, because these 3 functions are not allocating anymore, but this one is still, and this one is recursive as well. So there is still some allocation. So maybe we should have an intermediary functions, and this one would be the recursive one, and that would allow it. We wouldn't have to make recursive as well, but this is still an improvement. I don't want to spend too much time on this one. That was not the objective, so I'm just going to leave it up there. Just cargo check, see if it works. It works. Alright. So yeah, so that was protocol. Now we have the actual worker. So the actual worker, the ledger worker, is the owner of the ledger state. So the ledger state is stored in this actor, in this worker, So if you want to access it, you would have to send it a message. So the way it's done is that it has two different events. It has the confirm one that takes a milestone and tries to confirm a milestone. And then it has a get balance one to be able to access the inner state. And it takes an address and it takes a sender to be able to have access to the answer. It is done this way because it avoids having like some sort of locking mechanism, some sort of mutex or whatever, because if you want to confirm and access the ledger at the same time, then you need to have some locking mechanism. But by doing it this way, by having an actor that actually contains the state and works with messages, you have the guarantee that the messages will be serialized, so they will all come one after the other. So you are sure to not have any concurrent access to the ledger state without having the need for mutex or whatever. So this is pretty nice. So yeah, we have two events, confirmed and get balance. This is the actual running method. It just loops on the events, match on the events, and depending on what the event is, call the appropriate function. So on the confirm event we have the confirm method, and on the get balance event we have the get balance method. The get balance method is very simple. We are just taking back the one shot, the channel, and we send the answer. So it's just a get or zero on the state. So get or zero, we saw it earlier. If there is something, it returns the balance. If there is nothing, it returns zero. This is something interesting for Samuel, for example, because he's currently working on the API. So when he'll be doing a get balance API, this is very simple for him to implement, because you just have to send get balance to this specific channel, and then he would have an answer. So yeah, it makes it very simple for him. He doesn't have to take care of locking something, taking care of understanding if the state is already locked or not. He doesn't have to take care of that. It's already taken care of by the worker itself. But yeah, the important method here is the confirmation one. Here we just have a simple check that we are actually applying milestones in the right order. So we want to check that the candidate is actually the +1, so it's just the next one. Whatever happens in this function, if it fails, we are panicking here, because if something bad happens, it means that the coordinator approved something it shouldn't have. So it is a sufficient enough reason to shut down the node completely and to stop operations. Hopefully this is never happening. So there are a lot of errors that could happen, but yeah, it's just a safety net. Alright, so yeah, I'm going to speak about that. So basically this function is only just one method. It's visit bundle DFS, and that's the traversal I spoke about earlier. So this is the post order DFS, trunk first, branch second. So I'm going to look at this one. It's here in the traversal module. Yep, and that's this method. So it is very similar to the pseudocode that was in the RFC. If you compare both, it's very similar. Obviously this is pseudocode and this is Rust code, so you have a lot of differences, and we have a bit more checks here than in the pseudocode, but basically it's the same stuff. So I'm not going to explain how DFS work. If you're interested, there are a lot of very nice resources on the internet. But yeah, basically it just goes on all of the trunk and branches on a specific order. So this check just makes sure that whatever is being referenced as a trunk and branch is actually the tail of new bundles. So it prevents from weird bundle constructions where a bundle would approve something that is inside a bundle but not yeah, so we don't want these kind of things. So we only want bundles to actually approve tails, so the start of a new bundle. Then we check that it's not already confirmed, so that the specific bundle is not already part of a previously confirmed milestone. And then what happens is that whenever we have a new candidate, a new bundle candidate, we actually validate the bundle. This is very important for big design. We tried to make it so in the B code base that we don't have to deal with bundles as much as possible. So because bundles are going to be obsolete very soon in Chrysalis Part 2, so we try to reduce our usage of bundles as much as possible. And this is the only place in the B code base where you would see a bundle. This is the only place where we depend on bundles. So where is still, yeah, so the include is there, the import is there, and this is the only place in the code base of B where you find that specific import, other than the actual bundle crate, of course. But this is very important because it means that when time comes, when Chrysalis Part 2 is a thing, we don't have too much dependency to remove. So it will be very easy for us to switch because that's the only place where we would have to remove bundles. It has a small downside. It means that when we arrive in the confirmation, bundles don't exist. They don't already exist, so we have to construct them at this point, and it means that we have to do a bit more traversals that we would have to do. Another way of doing it would be to actually construct bundles in the protocol level. So whenever, for example, a new tail is solid, you know that a new milestone is there, and you could construct bundles there. But then you would have to have a bundle cache or a bundle storage or something like that, and we didn't want to have that. So for the cost of performance for a couple of months, we have the advantage of having less things to refactor. So we thought it was a nice deal to do that. So yeah, a lot more traversals but no refactoring. So yeah, we validate a bundle. Of course, if a bundle is invalid, same thing, we stop operations because it's not supposed to happen. And then we execute the onBundle callback. So I'm going to see this one a bit later. The last error that could happen is to, during the traversal, reach a transaction that doesn't exist or is not in storage. This is not supposed to happen because you only try to confirm a milestone when it's solid. So you know that you already have all of its passed. So this is not supposed to happen, but as a safety net, it's still there. Yeah, so as we said, trunk first. So you see that we always push trunk first and then branch. Yeah, and that's pretty much it for this traversal. The important thing is the onBundle callback. So this callback is applied on a bundle. We get the mutations of a specific bundles. So the mutations are, it's a set of all of the change of balance of addresses induced by this specific bundle. So each value bundle is mutating some addresses. this function just return all of the mutations. So now that we have these mutations, we are going to try to apply them to the ledger. If there is a conflict, we don't apply them, otherwise we apply them. So first we check if it actually mutates the ledger. So this function returns two things: a boolean that tells if it actually mutates it or not, and it returns the mutations. Because a bundle could have mutations, but without mutating the ledger. So it's a bit weird, but if let's say in the same bundle you send token to a specific address, but then you get them back or something like that, there are some mutations, but they all sum up to 0. So you don't actually mutate the ledger. So if that happens, then this is a zero value bundles, and data bundles, data transactions, for example, are also zero value bundles. So we just increment this in the metadata, and then we automatically go here. I'm going to check this one a bit later. But if it mutates, if it actually mutates the ledger, then we do this part. So we go through all of the mutations. So we loop on the mutations. We get or zero the state for that specific address, and we add the difference in it. So now we know the new value of the address. If the new value of the address is less than 0, or if it's more than the IOTA supply, then it's conflicting. So we set a flag, we increment the number of conflicting bundles, and then that's it for this for. If it's not conflicting, then we do a second pass, this time to actually apply the modifications to the ledger and to the difference in the metadata. And we also include this tail hash to a set of included tails. We have to keep track of the included tails because they will be needed to actually compute the Merkle proof we have been talking about. So we have to keep track of all of the tails that have been included in the ledger. Then when all of this is done, whatever happens, we increment the number of referenced tails, and then we update the metadata of this specific tail. So if it was conflicting, we update its conflicting flag. Whatever happens, we confirm this specific bundle, we set this confirming milestone index, and we also set this specific timestamp, the timestamp of the confirming milestones. Some things that are not done yet is to set some metadata for the tip selection algorithm, so the OTRSI, YTRSI, or something like that. If you want to learn more about the new tip selection algorithm, you have this RFC. But there is a notice here that says that it's deprecated, it's going to change a bit, so I think a PR is being opened these days, so yeah. But if you want to at least have some definitions that are not going to change about what I just talked about, OTRSI, YTRSI, that kind of stuff, it's in RFC 8. So yeah, this is still to be done so that Samuel, working on the tip selection algorithm, can have access to these fields, because he needs to propagate them, but they need to be first set, so it's where that would be set. And that's pretty much it for the traversal. It's nothing much, to be honest. It's just a traversal with a very specific order. And yeah, and that's it. And depending on if it's mutate or not, we include them or not. So yeah, that's the traversal. Then we have this metadata struct that contains some stuff that will be interesting for third parties that are interested into into having access to some statistics or whatever. So this is being updated whenever we do the traversals, and at the end of the traversal it will be converted into the actual event and then dispatched. Yeah, here nothing very fancy, just a new function. If you don't know this syntax, it's pretty nice. It allows you to create a struct, for example, by only a subset of its fields. So here I'm just specifying index and timestamp, and I'm saying that whatever are the other fields, they are just default values. So if you don't know this syntax, it's pretty helpful. Yeah, this is what I talked about when doing the traversal and not having bundles outside of this crate. It means that you have to actually construct them. So this is another little traversal that from a tail construct a bundle. So it's going to basically traverse through the trunks. So visit parents follow trunk. So it's going to go through all of the trunks, and it's going to do that until it reaches the last index of the bundle. So basically it collects all of the transaction of the bundle, and then it returns the bundle builder. And then we have maybe I'm not going to speak about this one now. Let's finish about this. So if the traversal is fine, if it doesn't ends with an error, we do some stuff. So the first thing we do is to do the comparison of the Merkle proof. So we check the Merkle proof with this thing, and this thing is nothing more than actually computing the Merkle proof with the set of included tails. So we compare the one that comes from the milestone, which is this one, with something that we compute at this very moment, depending on all of the included tails. Obviously, if there is an error, as usual, we panic. Otherwise, we just do a log that we confirm the new milestone. We put some statistics, so the number of reference tails, the number of zero value, conflicting, included, that kind of stuff, and we also raised an event. So if there are some third parties plugins listening for that, they will be notified. Yeah, and that's pretty much it for this worker as well. I'm not going to speak about this one. That's just a ternary encoding that allows to go from bytes to ternary, and obviously there is an RFC as well for that. So if you want to know more about this specific encoding, have a read about this RFC. I see that we have 7 minutes left. I don't have much more to speak about. There was something I said maybe we would do, yeah, because I remember that this shouldn't be here. I don't exactly remember why it's here, so I'm going to change that. But if you have questions in the chat regarding white flag or regarding the ledger or whatever, that's the moment. We have 5 minutes left, so I'll be taking some questions, but at the meanwhile I'll be changing that. So now this would be a parameter of the actual worker. This wouldn't be there anymore. Where is the boss? The boss is there. Alright, then here we would have we need arch. think it's in sync. Sync arc. What's up? And then yeah, it's not part of white flag yet, but it's part of safe. Yeah, it's fine. And then we don't need white flag anymore. Yep, I guess it's fine. Yep, it is. So yeah, it didn't really need to be in this one, but this one it has to be somewhere, and it can't be on the worker itself, because from outside we don't have access to it, so it needs to be somewhere, so it needs to be owned. So at the moment it's there. Maybe it's going to change at some point, but yeah, that's the easiest way, at least, to prototype it. Alright, I don't think I have much more to do. Yeah, so it wasn't a live coding today. I just wanted to take some time to actually explain what white flag is, how it works internally, and how it's been done in the B project. So yeah, yeah, that's pretty much it. Maybe I'll have some questions in the chat. I'm going to wait a bit. Alright, seems like I have no questions. I hope it means it was clear. Alright, then I guess that's the end of the stream. We'll see you all next week for a new episode 11 of the B sessions. Thank you very much for joining, and see you next week.